So again, this is just a quick walkthrough video of the notes to supplement the information in the chapter for those of you who have been out. Section 4.2 is about the trigonometry for acute angles, specifically the reference triangles for 30, 60, 90 and 45, 45, 90 triangles. So some of our definitions for today, just to make sure we know what we're talking about when it comes to angles on a coordinate plane. Standard position for an angle has the initial side along the positive x-axis, the vertex on the origin, and the terminal side of the angle is measured in a counterclockwise direction. So we're going from the positive x-axis here, this direction counterclockwise. So if you think about a clock, the hands normally go this way. Counterclockwise, the way we measure angles, is the opposite, so counter of clockwise. Some more information we just need to remember. The vocabulary when it comes to a right triangle geometry and trigonometry. If this is angle theta, then this side is the opposite. This side would be adjacent, and this side is the hypotenuse of the triangle. So opposite of the angle we care about, opposite of theta, adjacent to theta or next to theta, and the hypotenuse. So we're going to define these in the words opposite, adjacent, and hypotenuse, but also with A, B, and C so that we tie back in Pythagorean theorem. So here are the definitions of your 6 basic trig functions. Again, here's my triangle so you can kind of see how I'm getting these. Sine, please don't say sin, it is sine of theta is opposite over hypotenuse. So it's the measurement ratio between the opposite side and the hypotenuse, or B divided by C. The way that you're going to remember this is with the acronym SOHCAHTOA. Sine is the opposite over hypotenuse. Cosine, don't say cos, this is cosine. Cosine is the AH part of SOHCAHTOA, so it is the adjacent side divided by the hypotenuse, or A divided by C. And tangent, not tan, tangent of theta is the TOA part, so opposite over adjacent. So whatever the opposite angle side is, or side length is, divided by the adjacent side length, or B divided by A. And then you have your inverse functions, your inverse trig functions. So cosecant is the inverse of sine. Secant is the inverse of cosine. And cotangent is the inverse of tangent. Now, tangent and cotangent, really easy to remember. The way that I remember which one's the inverse of the other ones is I think about it, the cos can't be together. So cosine cannot be with cosecant, it has to be with secant. The cos can't be together. Hope that helps you keep them straight, but cosecant is the inverse of sine. And since it's the inverse or reciprocal function, reciprocal means flip fraction. So all we have to do is literally flip the fraction from sine to cosecant. So cosecant is the hypotenuse over the opposite side. Again, secant is the inverse or reciprocal of cosine, so it is the hypotenuse divided by the adjacent side. And cotangent is the inverse or reciprocal of tangent, so it is the adjacent side divided by the opposite. Now these 6 definitions are going to be helpful because in the next few slides of your notes, we're going to be able to measure all 6 trig functions when given pieces of information. So for example, we were given this picture. We were given that the adjacent side is 21 units long and the hypotenuse is 29 units long. Before we can really get started on the trig measurements, because we know we need all 3 sides of this triangle, we're going to throw it back to Pythagorean theorem real quick and figure out what this opposite side length was. So very easily, okay, a squared plus b squared equals c squared. We can toss those numbers in after we solve for b, and we find out that b is equal to 20. At this point, all I have to do is sine of theta is equal to the opposite divided by hypotenuse. Cosine is adjacent divided by hypotenuse. Tangent is opposite over adjacent. So we're just taking those numbers from my triangle picture and putting them into the trig measurements. Cosecant is just the inverse of sine, so flip this fraction. Secant is just the inverse of cosine, so flip this fraction. And cotangent is the inverse of tangent, just flip this fraction. We can do the same thing if given one of the trig measurements, because truly that is the same as giving me the picture they just did. They're still giving me 2 of the sides, the hypotenuse and the opposite, since this was sine. And we can use Pythagorean theorem to solve for the side that we're missing. Now, a couple notes on this. Whenever you are going to do the square root of the number, if it doesn't come out to a whole number, like if it's actually irrational, I need you to go back a step and just leave it as the square root of whatever is underneath the square root. So 6 squared divided by 5, divided by 6 squared minus 5 squared is 11. So we're just going to say that the side length A is equal to the square root of 11. And after that, I can start doing my trig function. So again, cosine is the adjacent divided by the hypotenuse. Tangent is the opposite divided by the adjacent. But you'll notice here I have to do an extra step. This is called rationalizing the denominator. Your book actually leaves its answers like this, but in correct, good mathematics where we're headed with these numbers, I know that we're going to need to rationalize the denominator. So you're going to multiply both the numerator and denominator by this denominator here. Because essentially what's going to happen is square root of 11 times square root of 11 becomes square root of 11 squared. Because it's multiplying twice, right? Square root of 11 squared. So the square root and the square cancel out. You have 11. All I've done is basically get rid of the square root in the denominator by multiplying a scalar, 1, to both sides. And you can kind of see what happens after that. Some things I want us to remember as well are special right triangles. We have our 45, 45, 90 and our 30, 60, 90 triangle. If we let the side lengths of the 45, 45, 90 triangle be 1, then we know through Pythagorean theorem that the hypotenuse is square root of 2. So this is kind of like the most basic 45, 45, 90 triangle. All of the rest of them are just scaled up versions of this one. So this is the basic relationship between all of the side lengths there. Additionally, with 30, 60, 90, if we do the same thing, if we allow this side across from 30 to be 1, and kind of just follows to make the numbers make sense for the definitions we use, if we let across from 60 be square root of 3, then when we use Pythagorean theorem, the hypotenuse is going to be 2. And again, this is kind of like the most basic version of this triangle. Everything else is a scalar multiplied of that one. And this allows us to write definitions for all our trig functions and solve them very quickly in our head. So here's us solving all of the sine. For the reference triangles, for the special right triangles, you're going to have 30s, 45s, and 60s. Remember that we can measure this in degrees or radians. And so you see that there to help you memorize it. This in purple here, after you figure out all the definitions, is a trick for your hand. And I am probably going to make a separate video for this because I can't show you my hand when I'm recording on my iPad here. And when I get back to the classroom, I'll try to make that video for you to show you how to use your hand to do these reference triangles, trigonometry. But go ahead and have this in your notes so that it's there for you. The square root of the below fingers divided by 2. You can see the definitions here. I'm not going to spend a lot of time on it. Then we went through and did the same thing for cosine, getting definitions for these particular triangles, which allows us to do this trig in our head without a calculator. For the hand trick, again, I will explain that in a different video, but it's the square root of the above fingers divided by 2. Tangent, same thing, opposite over adjacent, Rationalize denominators when necessary, and the relationship with the hand thing relies on the fact that tangent can be defined as sine divided by cosine. So that means we're going to do the square root of the below fingers, which was sine, divided by the square root of the above fingers, which is cosine. Again, won't make sense to you. You can see me showing you my hand, which I will do in a different video. But those are our definitions for the different degree measurements for sine, cosine, and tangent. Obviously, those inverse functions are just the reciprocal of each of these fractions, so we're not going to put those in our table. This table might be super important to make it look nice because this will be helpful and things we need to memorize, either straight memorizing them or with the hand trick that you will see in another video, or some other way that you learn to memorize these 9, measurements and what they are in radians and degrees for the 3 trig functions. Okay, so if I ask you to evaluate without using a calculator, either refer to the table or use the hand trick to kind of get these particular things done. We had a challenging one here with cosecant and secant. Remember, cosecant is 1 over sine. So if I'm doing cosecant of 45, it's like 1 over sine of 45. And if you don't remember just to use the reciprocal of sine of 45, here's the math that gets us there. If you divide a fraction in your denominator, you take the denominator of the denominator and bring it up to the numerator. That is fraction division rules, which I can show you if you want to see more. And then rationalize your denominator. Bing, bang, boom, we get square root of 2. Secant of pi over 6, which is like secant of 30, which is like 1 over cosine of pi over 6, which is 1 over cosine of 30. Well, cosine of 30 is square root of 3 over 2. That's what I know based on my hand trick. And then I just flip that fraction over to actually divide these two fractions is what I should say, actually. And then rationalize your denominator. But if it's not one of those particular angle measurements, if it's not 30, 45, 90 technically, or 60, we will be able to use a calculator. The one caveat to this is that you really have to check the mode that you're in. Like I said, I think in the last video, the book does a really good job of remembering to put the degree symbol when it's a degree. I don't always remember, but I say it out loud, so do as I say, not as I write, but I'm trying to get better at that. And if this happens, there's a whole sine, cosine, and tangent buttons on your calculator that you can use. Just double check that you're in the correct mode. And if you need help changing the mode of your calculator, I can show you how to do that. The reason that I'm making such a big fuss about checking the mode and making sure it has the degree symbol if it's degree is because just saying sine of 2, that's a radian measure. If you changed your calculator into radians, this is what you would get. But if you changed it into degrees, you'd get 0.034. It doesn't give you an error because you can still take the sine of 2 degrees. You're just taking the wrong angle measurement. So double check what you're measuring in degrees or radians, and then double check your calculator. Okay, so here's kind of working backwards. We're asked to find the angle that satisfies the given equation for theta in both degrees and radians without the use of a calculator. I like using the hand trick for this, and again, I know I can't show you that right now, but if you refer to that table, if we have sine of theta equal to 1/2, well, 1/2 on my table appears when theta is equal to 30, or pi over 6. So that's what theta's measurement is. To get 1/2, the angle measurement would have to be 30 degrees, or pi over 6. If tangent of theta is equal to square root of 3 over 3, we rationalize that denominator to get 1 over square root of 3 to help us with the finger trick. We would know that's 30 degrees as well. And cotangent of square root of 3 over 3, which is, again, unrationalize it, 1 over square root of 3. But remember, cotangent is just the inverse of tangent. So really, it's like asking tangent of theta equal to the reciprocal. Flip that over. And that's in my table. And so I know that theta is 60, or pi over 3. So it's really just working backwards and getting used to knowing the trigonometry of those different angle measurements of the special right triangles for sine, cosine, and tangent, and thus the reciprocals. But here's where it gets really fun. So when we started this problem, we were given this picture with a 90 degrees, angle beta, angle alpha, and side A, B, and C. And we wanted to know all of the unknown parts. We were given 20 for alpha and 12.3 for side length A. And that's all the information I need to be able to find all of the measurements, because I have trigonometry relationships between all of the sides and one particular angle. So if I know an angle and a side, I got the rest of them. We actually started this one by finding angle beta, because if this is 90 and this is 20, then this has to be 70, because all three angles in a triangle have to add up to 180. So we have that. We just need side length B and side length C. Now, there's like a million ways, not a million, that's dramatic. There's a bunch of ways that you could use the trigonometry of what you know to find these measurements. Here's what I chose to do on this problem. I chose to remember that tangent is a relationship between the opposite and the hypotenuse. Sorry, nope, opposite and the adjacent. Tangent is opposite over adjacent. So here's my angle alpha, which is 20 degrees. I know that the opposite, 12.3, which I was given, divided by the adjacent. Well, I know the angle measurement and I know opposite, but I don't know the adjacent. So I can rearrange this equation to solve for b. Multiply by b on both sides, divide by tangent of 20, throw that into a calculator, and I'd get 33.79. Now we rounded this number, so while I very well could use 12.3 and 33.79 with Pythagorean theorem to find the hypotenuse, I rounded this number, so it's going to be off by some particular degrees of measurement because of rounding. So stick with trig when you're trying to find the last angle measurements. Now again, you could use angle 70 degrees, but I'm going to stick with using angle alpha. There's two relationships I know that give me one of my known values and the hypotenuse. I chose to use sine, which is the opposite, divided by the hypotenuse. Okay, so sine of 20 is equal to opposite, 12.3, divided by the hypotenuse. I can then solve this equation for c, multiply by c on both sides, divide by sine of 20, throw that into a calculator, make sure your calculator's in degrees, and you get 35.96, which is the last measurement of this triangle that I was looking for. So trig allows us to do a lot of different angle relationships and side length relationships with very little pieces of information, which is just cool.